Relativity. The twin paradox. Hello, we are going to talk to you about special relativity. There remains a small point to clarify, and it is the paradox of the twins proposed by Paul Langevin at the Congress of Bologna in 1911, and not really resolved. This paradox tells that at the age of 20, twins separate, one of the two goes on an interstellar journey in a rocket moving at a speed close to that of light. The other remains on Earth. The speed of the rocket compared to that of light is such that the dilation of time seen from Earth makes 1 second for the rocket last 2 seconds on Earth. After 20 years, the Earthlings see the rocket make a U-turn and return to the same speed to arrive 20 years later. The journey took 40 years. The twin who remained on Earth is 60 years old. He welcomes his traveling brother, who has only traveled for 20 years due to the time dilation that has been observed. He is therefore 40 years old. The paradox lies in the fact that according to Galileo's principle of relativity of motion, we can also say that the traveler remained motionless in his own frame of reference while he saw the Earth moving away at high speed with a dilated time that returned after 40 years of his local time and whom he had seen aged only 20 years. Seen from this angle, the traveler is 60 years old and his brother who remained on Earth is 40 years old. Who is right and who is wrong, we could have left it at that, but a clever one pointed out that each of the twins lived 40 years in their own local time of their own landmark, and that they are therefore both 60 years old. After several debates, it emerged that the most shared opinion is that of the traveler who has aged the least. The argument given is because it was he who underwent positive accelerations to reach a very high speed and negative ones to stop, and likewise to return. In fact, the question related to the inertial frames of special relativity, in a straight line and without acceleration. It was at the end of 1915 that we could speak of the influence of gravitation and accelerations on the passage of time. The acceleration phases are to be neglected. If we are only interested in the inertial part, time passes there in the same way as on Earth. We want as proof of this what Albert Einstein wrote in his founding article of Special Relativity, entitled On the Electrodynamics of Bodies in Motion in paragraph 2 on the relativity of lengths and times of his first chapter Cinematic Part. In his introduction, Einstein posed the two fundamental postulates, the relativity of motion applied to electromagnetic phenomena such as induction, and the absolute constant of the speed of light, therefore of the electromagnetic waves of which it is a part. If you can read this article, you will notice that in its introduction it makes two important criticisms concerning its two postulates. Then he defines the notion of simultaneity by associating a local time to each event, time obtained by using synchronized clocks. On this occasion he defines synchronization as the fact that the time taken by the light to go from a clock A to a clock B must be equal to the time it takes the light to come back from B to A. This means that B indicates the same time as A, when the light arrived, and that the distance between clocks A and B remained unchanged throughout the operation. Paragraph 2 on the relativity of lengths and times examines how to measure a rigid rod from its own frame of reference, whether it is seen in motion or not in relation to other frames of reference. This is the case, A. Einstein writes. The observer provided with the ruler to measure moves with the rod to be measured and measures its length by superimposing the ruler on the rod, as if the observer, the ruler to measure and the rod are at rest. This is the case of the twin who travels. He measures lengths which remain unchanged, no contraction or dilation, and the same for time. Galileo's principle of relativity. It is impossible to demonstrate a uniform rectilinear translation movement by an experience taking place in the frame of reference of the moving object without referring to the outside world. Motion inertial is like nothing. Einstein then examines case B, where the observer is in a frame of reference and the rod in another frame of reference in motion relative to that of the observer. The observer determines at which points of the stationary system are the ends of the rod to be measured at time t, using the clocks placed in the stationary system, the clocks being synchronized as described in 1. The distance between these 2 points, measured by the same measuring ruler, when it was at rest, is also a length, which we call the length of the rod. Seen from the frame of reference of the observer deemed immobile by convention, we observe the light which goes from A to B. It turns out that the end of the rod, B, seen from the frame of reference by convention immobile of the observer, moves away at the small speed v, speed of its frame of reference relative to that of the observer. This delays its arrival at B as if the speed large v, of light had been reduced by the speed small v, of the reference frame in motion. Note that in his 1905 article Einstein designates the speed of light with a capital V. On the return to A it is the opposite. A approaches at the speed small v and the light arrives there faster with a speed seen by the observer of large V and small v. The observer of large V and small v. There is no ambiguity. Einstein distinguishes what we observe in his own frame of reference, which remains unchanged whatever the speed of the other frames of reference, from another referential in motion relative to that where the rod and the clocks are located. A desynchronization of the clocks and a change in the lengths in the direction of the movement are observed. In the following paragraph, Albert Einstein establishes the transformations to be applied to pass from the coordinates of the reference frame in motion to those of the frame of reference of the motionless observer by convention. It uses a point x prime of the moving reference frame at speed v with respect to the immobile reference frame, x prime, which moves at the speed minus v in this reference frame. The point x prime is immobile in the observer's frame of reference, so we can associate a clock with it. We will not detail this passage further. Einstein arrives at the same formulas as the transformations of Hendrik Lorentz finalized by Henri Poincaré. There is no plagiarism since the Lorentz transformations result from the contraction of the arms of the interferometer of Michelson and Morley, whereas Einstein reasons from the universal constant of the speed of light. Michelson and Morley's experiment was doomed because they were looking for an ether that was immobile relative to the solar system and the fixed stars. With the discovery of galaxies around 1920, it became clear that the stars were not fixed and that such a frame of reference was unsuitable. Our purpose is not to challenge special relativity, and even less general relativity. Albert Einstein remains our reference, including in the restoration of the ether with the article he published in 1921 entitled Ether and the Theory of Relativity. In this article, he adopts the new ether of Hendrik Lorentz stripped of all his physical characteristics except his immobility. Immobility that he refutes to make the ether compatible with the theory of relativity, but unfortunately, he cannot attribute to it a particular state of motion, and he decrees that this motion is indeterminate.
This is a copy of a talk given by Albert Einstein to the University of Leiden on May 5, 1920. The last paragraph of the talk reads as follows. Recapitulating, we may say that according to the general theory of relativity, space is endowed with physical qualities, in this sense. Therefore, there exists an ether. According to the general theory of relativity, space without ether is unthinkable, for in such space there not only would be no propagation of light, but also no possibility of existence for standards of space and time, measuring rods and clocks, nor therefore any space-time intervals in the physical sense. But this ether may not be thought of as endowed with the quality characteristic of ponderable media, as consisting of parts which may be tracked through time.
We note that for the speed of light to be the same constant in all the landmarks, the ether in which it moves must be motionless in all the landmarks regardless of their movement. We have a hypothesis that solves this seemingly hopeless problem. A very simple hypothesis deduced from the wonderful idea of Einstein in 1907 when he realized that free fall in a gravitational field is equivalent to an inertial reference frame. The simplicity of this hypothesis is such that it only takes 2 sentences to explain it. A. Ether is matter energy and as such it is in free fall in all gravitational fields. 2. Because of this, the ether is motionless with all bodies in free fall. We talk about it in more detail in our 2022 publication, The Ether of Albert Einstein, published by Bot. You will find experiments to carry out to verify this hypothesis. Thank you for your attention.